Hi, everyone, and welcome to the third and final workshop for AI for Social Good. This workshop will be focused on natural language processing, and I wanted to also quickly reintroduce myself. My name is Karan, and I helped start the AI for Social Good class at Stanford with Shubhang, and I was co-instructor for 2 years. And now I'm a research engineer working at Google on privacy-preserving machine learning. So I'm excited to welcome you guys back. And before we start, we have our normal housekeeping items. Especially important is following along with the exercises. So we have the link at the bottom. And let's get started. And so the motivation for today will come from trying to better understand and model fake news. So we know fake news has had an important impact on our discourse. We know it's been weaponized against us in the past. And so as natural language processing practitioners, it's important for us to better understand how fake news is, how it can be generated by natural language processing models, and how we can defend against it. And so that'll be the focus for today. And so as a little bit of background on why this is kind of timely, disinformation has been used against us in the past for influencing US elections. So on the left, we have a bunch of articles exploring the extent to which fake news might have impacted the 2016 presidential election. And on the right, we have a few articles saying that this might be happening again in 2020. And so we know this is an especially timely time to be thinking about disinformation. And so that's the one reason why we're thinking about it. Another reason to think about it is in the context of AI. So more sophisticated AI models can be used to generate automated disinformation. And so this has been something that's been coming up in the media recently in the last few years. And so this is what we'll be discussing today. And so what we'll be focusing on today is language models. So these language models basically take in some human written text, so maybe it's like a title of an article or something like that, and then generate sentences or paragraphs that can kind of complete the prompt given. So for example, you give it a fake news article title and then generates the rest of the fake news article. So we can see how easily this can be used to generate fake news articles as long as the quality is good, people believe it. And so there's been a lot of concern recently about more sophisticated language models and the potential for them to be used against us to generate fake news, which we'll be discussing today. Another couple things I wanted to flag were deepfakes, which can be used to swap faces and voices with anyone. And so I'll show an example in a second. And lastly, generative adversarial networks, which can be used to generate new images, for example, images of new faces of new people. And again, all these technologies can be used automatically to produce automated disinformation campaigns, which is pretty worrying. I want to show this example of a deepfake. This is Jordan.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, I don't know, Killmonger was right. Or,
so this was actor and director Jordan Peele, basically switching voices and faces with Obama. And we can see how surprisingly plausible it actually looks. And this was actually 2.5 years ago. And so like the technology has definitely significantly advanced since then. But as I mentioned, we'll be focusing on language models today. And kind of the context here and the way the automated disinformation coming from language models has kind of appeared in the public consciousness has been through GPT-2 in the beginning. So GPT-2 is a language model produced by OpenAI, which again basically takes in some human written text, some prompt. So this example involves a herd of unicorns living in some mountains, and then produces some completion of that prompt, so some paragraphs or some article basically about that prompt. And so in this case, this popular example was around like how this herd of unicorns was discovered or something. And you can see how surprisingly plausible it is. And this kind of started a lot of discussion around whether these kind of models should actually be released or not, or released slowly, or released with smaller models first, or whatever it is. And so this is something that we'll be discussing today, and our guest speaker, Rowan, will have more to say about this as well. So more recently, OpenAI has released GPT-3, which you guys might have also heard about. And this model is basically a much larger version of GPT-2. And kind of the key thing that happened here was scaling up this model was able to, the researchers were able to get a model that was able to produce surprisingly good results across a variety of tasks, even if you don't have that much training data for the specific tasks. So for example, for the task of taking natural language and producing shell commands, this model was used for this. And so we can see the user is typing in commands in natural language, and it's actually producing like normal looking bash commands. It's actually working. That's a pretty complicated command saying git clone something, install something. And so it's surprising that it even works at all. And so this model, there's been a lot of discussion around how this model should be released as well. There are a lot of also, by the way, a lot of other cool people doing demos showing, for example, this can be used to generate code as well. Yeah, and so this has led to a lot of discussion around whether this model should be released and how it should be released. And so we'll discuss this a little bit more with our guest speaker, Rowan. But I want to give an outline for today. And so we'll start today by talking about natural language processing, what natural language processing looks like, how we can take our picture of deep learning that we've been using for the last couple of weeks and apply it to natural language. Second, we'll be talking more specifically and formally about what we mean by a language model. Third, we'll be talking about recurrent neural networks and other models that implement the language modeling paradigm. And so we'll learn how these models are kind of designed. And lastly, we'll show how easily these models can be used to actually generate fake news. So by the end of today, we'll show that we can generate some semi-plausible kind of fake news using a relatively simple model in a Colab notebook. And lastly, our guest speaker, Rowan Zellers, will be talking about using neural language models to actually defend against fake news, not to generate fake news. So we'll start today by asking ourselves a question which we asked kind of in last week's session as well for image data, which is how do we take our picture of deep learning and how do we actually deal with text data? So let's recap our picture of deep learning again. So the standard picture looks something like a deep neural network, which is a feed-forward neural network is another word for it, which has some input layer, which is a bunch of numbers, a vector of numbers. You apply some transformation to it, some linear transformation, followed by an activation to get some hidden layers. Maybe you repeat this a few more times. And then finally, you apply another linear transformation, another final activation, and you get an output layer. And so in the past, the output layer has looked like just one or two numbers representing kind of a binary classification task. This can also represent multiple numbers if you want to do classification over multiple things. So the final output layer can have, for example, 10 probabilities over 10 different items if you want to do classification over 10 different things. And so that's our general picture of deep neural networks. And so the first question we want to ask ourselves if we want to apply this picture of neural networks to natural language text is how do we actually take natural language and fit it into our input layer? So remember, our input layer just takes in a vector of numbers, and so text isn't numbers, and so we have to have some way of taking text, producing some numbers from it. And so let's look at this example prompt. I'll meet you at the airport in N. And so this is basically a series of words, and we want to be able to put this in our model in some way that our model can learn something useful out of it. And so we can represent each of these words with a variable x, x1, x2, x3, up to x8. And then we can try to put that into our model. But again, these are just text, and even if we put in IDs representing the words, it isn't really that meaningful. And so as a reminder of what we did during our first week to deal with a similar problem, we used techniques for producing word embeddings like word2vec and glove to produce vectors representing each number such that a vector has a similar position in some embedding space if the corresponding word shows up in similar contexts in some large corpus of data like Wikipedia. And so if you have a word like good and you have another word like great and they show up in similar contexts, then they should have similar word embeddings. And the goal of our model is basically to learn things on top of these word embeddings, and so that it can kind of properly learn things and it gets the information it needs. And lastly, so we have 8 word embeddings. These word embeddings might be like, each of them might be like 100-dimensional, for example. And so what we might do to get a final vector of numbers, if we want a single vector of numbers to put into our neural network, we might start by concatenating all these embeddings together. And so if each of these is 100-dimensional, we end up with an 800-dimensional vector, which we put into our neural network. And so that's how we'll start doing things. So this is what our input layer looks like. Next, so any questions on this so far? Cool. Let's proceed to the output layer. So the next question we have is, what are we actually predicting for our output layer? What does our output layer look like? And so the question here will be basically, given this text, what do we actually want to predict? So we have this text, I'll meet you at the airport in N, and there's a ... which is kind of suggestive of something, which is that we might want to predict the next word. And so the next word could be hour, it could be minute, or it could be automobile. And so a very natural task for us, given some series of texts, maybe a full sentence, is predicting the next sentence, for example, or given some phrase, it's predicting the next word. And so predicting the next word is an interesting task because it kind of proves that we can actually understand the text well enough that we can actually guess what the next thing is going to happen. And so if we have a model that's really good at predicting the next word, then we can say, hey, this natural language processing model actually really understands natural language in some way, which like maybe a simpler model does not. And the way this kind of relates to our classification problem is this is exactly a multi-class classification where the number of classes is the number of items in your vocabulary. And so if you're predicting the next word and there are like 100,000 possible words you might want to predict in English, then you're doing multi-class classification with 100,000 classes. Cool, and let's describe this a little bit more formally, what we mean by a language model, which I've been throwing around previously. Basically, the task of a language model, a little bit more formally, is given a sequence of words, x1 through xt, you want to compute the probability distribution of the next word, xt plus 1. So this is just an expression representing the conditional probability of xt plus 1, given that x1 and x through xt were the previous words. And so again, this is just another way of saying, given some previous words, we want to classify, produce some probabilities over the next words. So xt plus 1 can be any word in the vocabulary, w1 through wb. And if you look at some more context on this, we have some slides that we thought were helpful for understanding this material as well. Cool. So why do we care about language models? It turns out they're not just interesting because it's interesting to kind of understand natural language and be able to predict on it, but you actually use natural language models every day. So for example, Google Autocomplete, when you're searching something, it's predicting the next few words that you might want to type. On your iPhone or Android, you might be typing something and it predicts the next word as well, and so this is all powered by language models. Another really interesting thing about language models is that they can actually be used to generate new text, which is actually really relevant for our discussion today. So for example, if we have two words, which are human written maybe, today, the, and we have a language model which is really good for it's been trained so that it's really good at taking in some sequence of words and predicting the next word. What we can do is ask our language model, hey, the previous words were today, the, what is the probability distribution over the next word? And so the model will output a probability distribution, and so it's saying company is the next word with probability 15.3%, bank is the next word with probability 15.3%, and price is the next word with probability 7.7%. And so now what we might do is sample from that probability distribution and say, with 7.7% probability, what we'll do is take the word price, and we'll use that as our next word. There are also other more sophisticated techniques for kind of managing this probability distribution and sampling words from it, but this is what we'll do to start. And so now the next thing we'll condition on is the previous words, today, the price. And again, we'll ask our language model to get the probability distribution of next words. We'll sample from it. Now it's saying 30.8% probability the next word is of. And so we'll ask it again, today the price of, and it's saying the next word is gold. And so we can see how this can be used to generate arbitrarily long text. It can be used to generate sentences. It can be used to generate paragraphs. And we'll see that this can actually be used to generate fake news as well. And so it turns out that basically if you take this technique and scale it up, that you can actually produce pretty realistic text, which is kind of a surprising insight. So it turns out GPT-2 and GPT-3, which you guys have seen examples for now, are language models themselves in this sense. They're generative language models. It turns out that GPT-3 and GPT-2 is generative. And so scaling up this basic idea basically gets you pretty good results. And so this is another sample from GPT-3, which was around giving your snake a bath. And you can see how surprisingly plausible this one is. Here's a little snippet from it. Take a very soft toothbrush, soft, not hard, and scrub its scales. Scrub hard, but be gentle. So you can see how specific these instructions are. Cool. So I just wanted to summarize our kind of picture of what we're doing, our first attempt for how to do deep learning and on natural language processing. We take our input layer, we take a fixed set of words, let's say 8 words in this case. We produce embeddings for them separately using some word-to-vec technique or glove technique. And then we can those all together for a given sequence of words. And this is a fixed length sequence of words. Right now it's 8. And then we put that into our input layer. We do some transformations. We do some activations. And then at the end, we get a probability distribution over the next word. And so given that, we can do things like generate new text. We can power things like autocomplete, for example. And so this is how we're starting. And so now I wanted to kind of take a break from the lecture and go into the class exercises. So we'll now kind of complete some live coding exercises where we'll kind of apply the first picture of deep learning plus NLP, which we described earlier. And so we have this Colab notebook, which you can follow along with using the link provided in the slides. And so let's start this. And by the end, by the way, just as a teaser, we'll use a more sophisticated deep learning technique, basically, to actually generate new fake news using the kind of techniques that we've already mentioned. And so let's start by loading up our data set. This is a subset of a data set tagged as fake news by some independent third party around the time of the 2016 election. The data is basically this text file, and it looks like a bunch of fake news articles concatenated against each other. And so you can see the beginning of the first 3 articles here. You can see a lot of it is around like Hillary Clinton and Trump and so on, because it's around the time of the 2016 election. And so we can change the index to get different articles, for example. And you can see the last article changed. And so you can play around with the data set as well on your own copy. And so let's recap a little bit our setting and also talk about how our setting here might be a little bit different from the setting that I just presented. So the way we'll build our language model, remember, is in the past I presented it as predicting the next word given a sequence of previous words. What we'll be doing here actually is taking a sequence of characters and predicting the next character. So instead of predicting out of like 100,000 potential next words, we'll be predicting out of a set of 62 potential next characters. So that'll make things a little bit easier for us in some ways. But the task of the language model now is a little bit harder in some ways, because the language model now takes in, instead of words that have specific meanings and have embeddings, it'll be taking in just characters, and it'll have to take in those characters and learn something useful out of them. And then at the end of it is predicting the next words or sentences or paragraphs, character by character. And so if this model will give it a sequence of characters, we'll ask it to predict the next character, and then we'll sample from that distribution, and then we'll predict the next character, and then the next character. And so it'll be actually even a little surprising if it even produces plausible text, like if it even produces words that are coherent. But we'll see that it actually does, surprisingly. And so that's kind of the general setting. We'll cut up our corpus into chunks. So last time we previously discussed having chunks of 8 words, and then we put that into a model, and then we predict the next word. Here we'll be using chunks of size 40 characters, and then we'll put that into our model, and then it'll predict the next character. And so here what we're doing is just taking in our corpus and processing it, breaking it up into these chunks such that there's a chunk of 40 characters, and then we predict when we know the next character. So we take in a 41 character length. We take the first 40 characters and say, here's the context. And then the last character is the label. And we want our model to be really good at taking in context and then predicting the label. And so total number of characters in our data set is 62. So that's what we'll be predicting. The chunk length is 40, as I've mentioned. And the number of chunks given a corpus length of this much is 500,000 chunks. And so basically what that ends up meaning is we have around 500,000 examples where each of the examples contains 40 characters. And the number of characters possible is 62. And for our labels, for our Y, the shape basically looks like, again, 500,000 examples and then 62 possible characters. So now we're going to code up a Keras model, which basically takes in these characters and predicts the next character after each chunk. And so I've actually just pasted it in the interest of time to make this a little easier. Basically what we'll be doing here is we have a dense model, which is our normal kind of model, which takes in some input, and then apply some fully connected layers, which we've been discussing. In this case, the input will have shape the number of chunks by the number of characters. So the chunk length is 40 in this case, the number of characters is 62 in this case, and then we flatten this. What flatten means in this case is just concatenating all of the chunks, the characters together. So each of the you can imagine that each of the characters has a 62-dimensional embedding. Although the embedding in this case is just a vector with a 1 in a certain position representing the character. And so what we're doing is we have 2-dimensional embedding for each character. We have 40 characters. We're concatenating them together, and that's what this flatten layer does. And then we apply a dense layer, which is another name for a fully connected layer, with 128 outputs and has a relative activation. And lastly, we apply another dense layer, which has 62 outputs, the number of characters, and then has softmax activation. And softmax is interesting here because softmax is a generalization of the sigmoid activation that we talked about earlier. And the idea here is basically we end up with a probability distribution rather than just some random numbers from a neural network. And so we'll optimize our model using an optimizer called RMS-prop, which is an alternative to stochastic gradient descent. And we'll use softmax plus entropy as our loss. And so if we run the cell, it gives us a summary of what this model looks like. And so the flattened layer gives us a shape of 2480, which should be 62 by 40. And we have a dense layer, which gives us an output shape of 128. And we have a final dense layer, which gives us an output shape of 62. So this is all as expected. And the number of parameters in total is 325,000 in this case, which is maybe a medium-sized model, not too large. And now what we'll do is make sure our, by the way, a quick sanity check is making sure the number of parameters for each layer makes sense. So you can see that the number of parameters for the first dense layer makes sense if you calculate the number of parameters required for the weights and the number of parameters required for the bias. And similarly, the second dense layer, again, if you calculate the number of parameters for the weights plus the number of parameters for the bias, will give you exactly this number. And so now what we'll do is just make sure this is all working, and we'll try training our model for a little bit to ensure the loss decreases and everything's working. So we can see the loss decreasing a little bit slowly, and so this is a good sign. This means that our model is able to be trained. And there's no bugs in it, hopefully. Cool. And so now we'll come back to this notebook when it's time to play around with a more sophisticated model, and we'll actually show that this type of model can be used to generate fake news. But for now, let's go back to our slides. Cool. So just recapping this picture again, we have an input layer which takes in some word embeddings, we concatenate them together, we put them in to dense layers, and then we have an output layer which gives us a probability distribution of the next word. So the next thing we want to do is actually improve upon this, because it turns out this is not the most successful technique for training language models. It's not a technique that models like GPT-2 and GPT-3 use. And so we'll build up to more sophisticated techniques. So let's start by thinking about what's wrong with our model. So looking back at this picture, I think the most obvious thing is that the input layer takes in a fixed set sequence of words. So for example, in this case, if it takes in 8 words and it only has weights corresponding to 8 words, and so if you put in 10 words, it won't work. If you put in 6 words, you'll have to pad it, and it won't really work that great either. And so this is not ideal. And so, so basically, the problem with this model is that it takes in a fixed sequence length of words. So ideally, we can put in sentences, we can put in phrases, we can even put in paragraphs, and our model is still able to predict the next word or sequences or paragraphs. So just to summarize, the problem is that the window size, which is the kind of the context size, the size of the number of words, the number of characters, in the case of the collab, is fixed. If we want a model that's really good at predicting the next word, we want a model with a really, really large window size. And so, but even if we made the window size really large, let's say it's like 100 words instead of 8 words, it can really never be big enough, right? And if we want a model that's able to really predict really plausible text, it needs to be able to model long-term dependencies, and this is a really important concept in more sophisticated natural language processing models. And so it turns out that as long as you're making the window size finite, it can really never be big enough. And the last point, which is a little bit more subtle, is that weights are actually not shared between time steps. So if we look back at this picture, the input layer and the dense layers, specifically the first dense layer, has weights that are specific to each of the positions, the 8 positions for each of the 8 words. So there are weights corresponding to E1, there are weights corresponding to E2, but in general, it seems like we don't really want to waste parameters and have a completely different set of parameters for each possible position in the sequence, because it doesn't really matter too much whether the position of a word is like in the position for the 5th slot or the 6th slot, for example. And so ideally, we have a model that kind of knows that it doesn't really matter kind of the exact position of the word as long as we can still model kind of the general sequence. So ideally, we have a model that's actually sharing weights between time steps, and that'll actually result in a smaller model that actually still performs better. Any questions? I saw there were some questions in the chat as well. Sounds good. So the next question we want to ask is, how do we actually share weights across time steps? What does that look like? And so this is actually a motivating question behind a technique which has been popular in the past for natural language processing, which kind of like brought natural language processing to up to speed compared to like vision techniques in the past. And this is recurrent neural networks. And so I'll present kind of a general picture of recurrent networks first, and then we'll talk about specific details related to how we actually implement this for language modeling. And so the way this will look like is we have some input sequence, which again has some word embeddings, E1, E2, E3, E4. This can be any length now. It doesn't have to be specifically 8, for example. And then we'll somehow encode them as hidden states, which are themselves sequences of numbers. So H1, H2, H3, H4 are sequences of maybe 50 or 100 numbers. And each of them will be a function of the previous hidden state as well as the current input at the current time step. So for example, H2 is a function of the value of the embedding at E2, the input at E2, and also the weight at H1. And so the idea here is that the hidden state at each time step represents a summary of the information learned from looking at the previous time steps as well as the current input. And so if we ask our model some questions around what is this, if we do some transformation on top of the final hidden layer, the idea is that we can get some interesting information about potentially what that sentence represents and maybe the next word. So that's kind of the motivation around how we actually make this happen for language modeling. So now I'll present a little bit more specific picture around how we can apply vanilla RNNs for language modeling. And so again, we have a sequence of inputs represented by these input embeddings, E1, E2, E3, E4. This can be of any length. And we have an initial hidden state, which can be initialized to 0, for example. And then our trainable parameters look like these WH and WE, which are weight parameters, kind of similar to the weight parameters involved in dense layers, as well as a final bias for each hidden layer. And the way we compute the hidden state at each time step, which is again the key to kind of computing the computation in a recurrent neural network, is we do WH times the previous hidden state plus WE times the current input plus some bias. So again, the hidden state at each time step represents a summary of what the model has seen so far. And the way we compute it is by taking in the previous hidden state, which represents the previous summary of what the model has seen so far, as well as the current input. And then we multiply them by some weights and bias, basically. And we also apply a sigmoid activation, which we saw in the first week as well. And so in the end, we end up with a hidden state for each of the time steps. And now what we can do is for the final hidden state, whenever that happens, it could be after 4 steps, it could be after 10 steps, whatever it is, we apply a final dense layer, a final fully connected layer, represented by weights U, which gives us a prediction in terms of the probability distribution over the next word. So remember, the hidden state H4 represents the model's opinion of what it's seen up to the 4th time step. And so now that hopefully contains all the information we need to predict the next word. And so if we just apply another dense layer on top of that, we can predict the next word. And so looking back at our problems that we discussed with our model, now all of them are solved, or they seem like they're solved for now. So window size is no longer fixed, and so we can take in any number of words, 4 words in this case, or it could be 8 words, and the only difference is we apply the final dense layer represented by the matrix U. We apply that at a different time step. Again, window size can't be big enough. For now, it's actually basically infinite in a way, although we'll find out later that it'll still be a little bit difficult to model long-range dependencies with this type of model. And lastly, weights are now actually shared between time steps. So we mentioned last time the problem is that like each time step has its own weights, which is kind of wasteful. But now all the weights we need for our model are WH, WE, and U, and as well as the bias. And so this significantly simplifies the number of weights we need, and the weights are basically mostly shared between different time steps. So E1 doesn't have its own set of weights, E2 doesn't have its own set of weights. And so this also kind of helps us in terms of reducing the number of parameters we need. Cool. I wanted to also quickly mention different variations on this technique of recurrent neural networks. The formula which we showed earlier for computing a hidden state given a previous hidden state and a current input is what's called a cell, which is used in a vanilla RNN. But there are also different variations of this which actually perform better in most cases. So gated recurrent units are a little bit more complicated, but perform significantly better. And long short-term memory units are also a little bit more complicated. But basically the difference in both of these is a difference in how we compute the hidden state at each time step. And it turns out that long short-term memory in general is like a good starting point for your RNN models, and usually performs way better than vanilla RNN for modeling long-term dependencies. And so if you're generating text where your context looks like a long sequence of things, then usually a long short-term memory network, LSTM network, is the place to start. So why don't we start the part 2 of the class exercises, and this one would be significantly more fun. So here we'll be applying our knowledge of RNNs to actually build a language model for fake news. This is a way to make it really obvious that AI can be used for harmful purposes for generating fake news. And this will make concerns around releasing models like GPT-2, GPT-3 more clear why people are concerned about this type of thing. And so what we'll be doing is building an RNN in Keras, which is a technique we've been using. The model will be in LSTM, and what we'll be doing is adding a couple LSTM layers, stacking them on top of each other. And the final output will have to be a dense layer, which basically takes in, again, which basically outputs a number of characters, 62 in our case, and does a softmax activation to produce a probability distribution. So let's go through this code, which I've copy-pasted just for convenience. And so what we do is we have an RNN model, which is a sequence of layers. The layers basically look like the first LSTM layer, which takes in our input embeddings and then produces a hidden state with 128 dimensions. And the input shape, again, is the number, the length of each chunk, as well as the number of characters, which is, again, also the embedding length. And it returns basically a sequence of hidden states. And then this next LSTM, we build another LSTM on top of this LSTM, basically takes in the previous hidden states as the input items for the hidden states at each time step. So basically this LSTM takes in the input embeddings as input. This LSTM takes in the hidden states from this LSTM as input, and it produces 64-dimensional hidden states. And then finally, at the end, we take the final time step from this LSTM, the 64-dimensional LSTM, and then we apply a dense layer to it. This was represented by the matrix U in the picture. And then we apply a softmax activation, and then we again do RMS prop and do softmax loss. And so if we run the cell, we again get our summary. And so the first LSTM has an output which looks like the sequence length. Remember, it's outputting all 40 hidden states for a sequence length of 40. And then has a 128-dimensional hidden state. And then the second one outputs just the final hidden state with 64 dimensions. And then we have a final dense layer, which outputs a 62-dimensional output. And so if you actually look, this has the hyperparameters for this model are actually pretty similar to the hyperparameters for the previous model. So like we're using 128, for example. And the number of characters at the end is the same. The final dense layer is the same. But the number of parameters in total for our model is actually way smaller. It's about half. And so this is basically because we're actually sharing the parameters across time steps for our model, which makes it easier for our model to learn things quickly as well. So now what we'll do is try training the model for a little bit to ensure that the loss actually decreases like we did before. And so what it's doing here is taking in batches of size 128 and basically taking 1,000 steps, so 1,000 batches. So each batch has 128 different items, where each item is an example with 40 characters, and then predicting the next character. So we can see that the loss has been decreasing, although a little bit slowly because it's a more complicated model. It turns out actually training this model will take a while. And so what we did was we trained a model for this, model for you, as you can see the results. And you can see that this is the same model, has the same number of parameters. And so what we'll do now is run the below cell, which lets us actually sample text from this language model. And so what we'll be doing for this is taking a random chunk from our data set and then asking our model to produce a probability distribution of the next character. And then we'll be sampling from that probability distribution. And we have this hyperparameter, which is called diversity in this case, which refers to the tendency of the model to produce more or less likely characters. So if it is more diverse, it'll produce more novel text. If it's less diverse, it might be more plausible text, but it might be text that it's seen before in the data set. And so we'll sample from this model and see what kind of text it can generate. And so what it's done is it's taken in this context seed, which is 40 characters, and it basically tries to predict the next character repeatedly. And you can see it's predicting mostly words, but they're not super coherent maybe. But it's kind of even surprising that it even predicts actual words. So remember what it's doing is it's predicting words character by character and sentencing character by character. And so you can see it's not super plausible, but you can see how a more sophisticated version of this could actually be used to fool people. And so you can see one common thing that people discuss when they're looking at these kind of models is the extent to which these models are actually memorizing their training data. So especially for really, really large models like GPT-3, for example, the size of these models actually grows to the point where they're actually larger than the actual training data that they're trained on. And so you can argue that a lot of what they're doing maybe is just doing information retrieval, where they're retrieving things related to the prompts that you give it. Although most of the time the text that it generates isn't always exactly occurring in the data set. And so that's something that Rowan will also discuss as well in this guest talk. We'll also run this cell. Basically what this cell does is we give it a certain seed. Instead of it picking a random seed, we give it a seed, which in this case is Hillary Clinton is under invest. And we can see what kind of things it'll produce. You can also play around with this yourself and kind of seed it with your own text and see what kind of text it produces. Because this data set came from around the time of the 2016 election, you can see that what it's going to predict is around things around the investigation around that time. And you can see the kind of things that it's predicting. So most of these are actual words, which is somewhat impressive for how simple this model is. But it's not super coherent. Like it's not making coherent phrases, for example. But if you read this article without realizing there's a fake news article, you might actually think it made some sense in the beginning. And so you can see how scaling this up could be actually pretty dangerous. And so feel free to try this with your own seeds as well, and see there's a lot of 2016 stuff that's coming up again in these generated texts. Cool. And if you're interested in more, we'll have some further reading, which we'll mention in the slides as well. Let's go back to our lecture. And now that we've covered how easy it is to generate fake news using simple recurrent neural networks, I wanted to quickly mention additional problems with our model that kind of motivate more sophisticated models that have been used to generate, that have been used to produce even more sophisticated language models. So two issues that still exist. So one is that it's actually still really difficult for the model to remember what it's seen many time steps ago. So I introduced this problem as modeling long-term dependencies. Turns out it's still pretty difficult for a recurrent neural network model to do. And so this has been kind of a problem that people have been trying to improve for the last few years in natural language processing. And secondly, it's not very parallelizable. And so what the recurrent neural network needs to do to produce the hidden state at each time step is produce the hidden state at the previous time step, and then the hidden state at the next time step, and the hidden state at the next time step. And so this is not parallelizable in the length of the sequence. And so a lot of GPUs and TPUs and a lot of compute devices, they're actually really parallelizable. And if you have a model that is parallelizable, it runs way, way faster on these accelerators. And so that's motivation for trying to develop more parallelizable models. And so the principal technique for developing more parallelizable models has been attention. And so I'll give it a little bit of an intuition for attention. We won't cover it in much detail here. The idea is basically in self-attention, which is what we'll be discussing here, is let's say we have two sentences. The animal didn't cross the street because it was too tired, and the animal didn't cross the street because it was too wide. And what we want to do is we want to figure out what the next word is after it. What we can do is, what a human might do is, given the word it figures out what is the, in that sentence, what are the previous or next words that are kind of most related to this word, and we can use that to predict the next word. So for example, it in this case seems like it refers to the animal, and so because it refers to the animal, we can predict that the animal didn't cross the street because it was too tired, for example. And for this alternative sentence, because it was too wide, in this case, the it seems like it refers more to the street because it makes more sense that way. And so it seems like the model in this case has learned that actually it refers to street. And so basically what attention is, in general, is a mechanism for the model learning to pay attention to different parts of a sentence or a sequence at different steps in the prediction task. And so this attention idea is basically the main idea behind transformers. The title of the paper was Attention is All You Need. And so this transformers are a variant on deep learning technique for natural language processing, an alternative to recurrent neural networks. And the idea is basically, instead of augmenting recurrent neural networks with attention, which was a technique which was used for a little bit, actually just remove the recurrence entirely because it kind of is expensive and you have to compute things in sequence, and replace it with attention entirely. And so it turns out this is now the dominant paradigm in NLP. And so models like BERT and GPT-2 and 3 and Grover, which our guest speaker Rowan will discuss, all use larger and larger transformer models. And so the general picture of what these transformer models look like is they have an encoder step, which does the self-attention thing, which I mentioned earlier, in a little bit of provide a little bit of intuition to figure out what parts of the sequence to focus on. And then it does a feed-forward network or a dense layer, which is what we've been doing. And then it does some more attention stuff in the decoder, and then it does a feed-forward thing to predict the next word. So that's the general picture of this. And so as a summary, we want to discuss today the dangers of automated disinformation, why we should be concerned about this, especially because of more sophisticated language models, more sophisticated automated disinformation campaigns that are being run by different entities. And we also learned that language modeling of fake news is surprisingly easy. So over the course of this lecture, we learned about language modeling, what it is. We also learned about techniques for language modeling. And we also built a relatively simple language model that could actually be used to generate fake news. And so this kind of gives more context to the discussion around whether we should be releasing models like GPT-2 and GPT-3. We also discussed recurrent neural networks. And lastly, we also discussed in a little bit of detail attention and transformer models, which have become the dominant paradigm in NLP recently. So if you're interested in this stuff, I wanted to give some further reading. All of this stuff is pretty approachable now, given the context you have. I recommend starting from the beginning if you're interested. A lot of these articles are kind of fun and provide intuition for why you would want to do certain things in RNNs and NLP and stuff like that. So I definitely recommend reading some of these links. And now I want to hand it over to Rowan to talk about defending against neural fake news. Thanks.
Okay, cool. Yeah, so today I'm going to be presenting, I guess, the second half of this workshop, defending against neural fake news. Yeah, so I'm Rowan. I'm a graduate student at the University of Washington, and I also work at the Allen Institute for AI. Yeah, and my interests are pretty broad, but I do a lot of work in natural language processing and computer vision. Yeah, so let's just get into it. So previously in this session, we learned about language models for generating news text. And so, right, like it's this high level idea, kind of like we learned this model such that we can flip a very high dimensional coin or a slot machine or whatever, and we can sample the next word from given a bunch of words x1 to x n minus 1, I guess. Cool. And you can use this to generate news text, like we showed earlier. And so I want to share one such article, kind of just like, some more information about me. Founder Rowan Zellers raises $11 million in Series A round for a startup offering ride sharing for dogs. So yeah, this is what I've been working on recently. Real dog ride sharing? Yes, please. Rowan Zellers, a founder at the Zoom stuff is hiding part of my screen. But anyways, yeah, so this is what I'm trying to say with this is that this seems like a realistic, relatively so, TechCrunch article about an Uber for dogs startup. Unfortunately, though, it's fake, and it was actually machine generated. And so kind of today, I'm going to be talking about this threat of neural fake news, and perhaps more importantly, how we can detect it and defend against it. So OpenAI, a year ago with GPT-2, loudly proclaimed that they had built a text generator that's too dangerous to release. They said that, and they gave a demo to journalists, and they didn't release like any of the model parameters or any of the pretty much anything to researchers. So we had some like scientific questions such as, is this really too dangerous to release, and how can we come up, like perhaps like the better question of how can we come up with a robust defense against it if it really is so dangerous? And so we have this paper called Defending Against Neural Fake News that we published in NeurIPS 2019. And so that's pretty much what I'm going to be presenting on today. But I'm going to make it somewhat high level and connected to some of the stuff we were talking about earlier, and hopefully like interactive and fun. So ask questions and all that. And unfortunately, I can't see the chat, so you might have to like raise your hand, or we'll figure something out.
Yeah, I'll make sure to keep an eye on the chat and the raising.
Thanks. Yeah. So let's kind of start by talking about some social good stuff. And this is one concept that if you I guess this kind of comes independent of the whole language modeling thing, and it's this idea of threat modeling. So threat modeling, according to the Wikipedia definition, is a process by which potential threats can be identified, enumerated, and prioritized, all from a hypothetical attacker's point of view. So this is a concept that people in the security community use to reason about things. And the idea is, let's temporarily think like we're an attacker for a second. Think about what they might do and what their motivations might be, and how can we come up with good defenses against it. So let's take a look back at GPT-2, for instance, and think, what would an adversary maybe a big government or a corporation that has access to a very large text generator want to do? Which is, might parallel existing actors who spread misinformation online. And so maybe just taking a step back, I want to define disinformation as fake news intended to deceive. So like you could say onion articles, clickhole articles, those aren't real, but they're not really intended to deceive. They're just satire. So that's we're kind of going to define that away. Cool. And so I'd argue that there's two main things that adversaries try and do. The first one is to just generate ad revenue by getting a bunch of people to click on their fake news articles. And the second one is to persuade people, which is to generate content that fits a given worldview, such as like, look at this scandalous thing that Barack Obama did or whatever. Cool. And I guess what I want to say is that for both of these, you need significant controllability. And so if we want to think about, okay, how dangerous is GPT-2 here at generating specific content that looks like real news and is to the standards of the person who's trying to like mass generate a bunch of, or organization, I guess, who's trying to mass generate a bunch of these articles? How would that work? So let's think about that for a second. So again, let's go back to that language modeling objective we were talking about earlier. And so what this does is it's going to generate a single text field from left to right. And one implementation detail that's kind of important is that we'll usually start with like a special start token, and we'll generate until we like hit a token that's called end. So that's like a special token, and it just means to stop generating, because otherwise you would just never know when to stop. You just like keep going and going, and you could always just sample another word. But once you see end, you're like, okay, that's the end of this part of this stream of text, if that makes sense. But suppose I wanted to generate some fake news like this. Like, okay, here's one that like presumably anti-vaccine people and organizations might want to generate, and that's a new study shows that vaccines cause autism. Okay, so it generates an article, but the problem is, if we're just reasoning about what this attacker might want to do, we can generate left to right, but this context at the beginning is going to stay there forever. So this context, or this like presumably like a headline type thing, it doesn't sound realistic. It doesn't sound like real news. And given that we're only generating left to right under the language modeling objective that we've set up here, we can never go back and change it. So that means I would argue that the threat posed by GPT-2 and GPT-3 is pretty limited by itself. And there's one other issue that I wanted to point out, and that's that news articles have a significant structure. So a news article isn't just a single field. It's actually a bunch of different fields. It has a domain, it has a date, has some authors who are real people, it has headline, and it has a body, or just, I guess, the main part of the article. And I would say all of these are really important. If you don't have some of them, I mean, maybe some are more important than others, but when we read the news or read other articles, we're kind of looking at all of these fields. And also, these news articles, these metadata attributes, I would say encode important attributes. So a Fox News article, that's going to look a lot different from a Wired article. An article written in 1994 will look very different from one that was just generated or written today. And depending on who the author is, that might actually really change the feel of the article. So what we did was we put on our hats and we're like, okay, well, how could we, if we wanted to, thinking like an adversary, what would an adversary do in order to modify this objective just a little bit to generate controllable content? And so we created Grover, which is this threat modeling prototype, and it stands for generating articles by only varying metadata records. It's a Muppet because that's how NLP, that's how NLP has worked for the last couple of years. It's a little weird, but we'll just roll with it. And so what we do, the big idea is we take this objective, which consists of a bunch of different fields, and we're going to decompose it in a flexible order. So each of these fields, we're going to give special start and end field tags. So the domain will be like start domain, and then the NewYorkTimes.com end domain. And we could do that with all the others, like start date, May 29th, 2019, end date. And now what we can do is we can just lay those out flat and then generate left to right. We can give it a new thing like start headline, and then we could sample from the model, and then just it'll give us what it thinks is a headline from New York Times written on May 29th, 2019. And so here's one thing that we could give it, and so on. And so this lets us perform a couple of interesting tricks. What we can do is we can go from the domain, the date, and the headline, and then generate the body. What we can then do is go back. We could even generate the authors if we wanted to make up some. And then we could even do is go back and generate the headline again and come up with a headline that sounds more realistic. So this fixes the problem I was talking about earlier today, which was, these the context is fixed, and so it's never we can never change it. So now we can change the seed context fields. And just to test this, we collected a lot of news data. We trained the model on all of that, and we used a very large transformer architecture, which we talked about earlier. And we considered 3 sizes, which were similar to the amount of compute and sizes that GPT used. So Grover Base has 117 million parameters, still quite a lot. Grover Large has 345 million, and Grover Mega has 1.5 billion parameters. So it's a pretty big model, and it costs roughly $25,000 to train. So just to test it out, so we had this model that we trained. We wanted to see how good it was, because OpenAI didn't release their model, so we wanted to test this. And so we consider this test. We take a real article, we take its domain, date, authors, and headline, and then we have a human written rest of the article or body, and a Grover generated body. And we're just going to compare those 2 articles and see which one humans like more, essentially. And so we compared it on a couple of different axes. The first one is style consistency. So like, is the article changing styles midway through? And they do about the same. The second one is how plausible the content is. So a little bit. So by the way, these are from 1 to 3, where 3 is better and 1 is the worst. So the human written articles are a little more plausible than the Grover written articles, and overall they're a little more trustworthy. So somehow, so the Grover articles often they're given a real context, and sometimes it's just not as good of a writer as humans are for that context. Cool. And so now this is the key question that we wanted to evaluate. Like, how good is Grover at writing propaganda? So instead, now we're going to come up with a propaganda or fake news domain, such as like a conspiracy theory website. We'll give it a date. We'll give it the fake news articles and the fake news headline, and then we're going to have the actual body that was written by a human. And then for making it, for the kind of trick that we're going to evaluate, we're going to replace the domain with an honest domain like the New York Times, keep the date, drop the authors, keep the headline, and then write a Grover written propaganda body. And now one last trick, we're going to rewrite the headline again to something that the model thinks is more realistic and news-like. And then, of course, we'll drop the domain because everyone would be like, oh, the New York Times is more reputable than the Natural News or some other propaganda website. So how good are the generations here? Using the same axes as earlier, here it's actually somewhat surprising. The Grover written propaganda is slightly more stylistically consistent. It has about the same level of plausibility, which I guess makes sense because it's both of these things are like just wrong. But what's kind of shocking to me, at least, or to us, is that it's actually overall more trustworthy. So people find model written news or propaganda more trustworthy than real propaganda. So this kind of set off some alarm bells at first, but maybe we can take a step back and realize, well, wait a second, like this kind of just is because in part that human written fake news is not very good or believable. Like this is this propaganda website I was talking about earlier, the Natural News. I mean, I don't know how popular it is, but this is just one example. And it talks about how vaccines have been based on medical fraud for over 100 years. This is probably not a real news article. And we don't even need to really deeply understand what this thing says. But just like, even stylistically, this just doesn't sound realistic. And so, but maybe we should take, but so this is what we then did. Before releasing the model or doing anything, we're like, okay, how can we stop this threat that we created with some minimal modifications, thinking about what an adversary might do, and how can we detect this if it were to exist in the wild, which people were worried that it might, be everywhere, I guess. And so here's a little bit more terminology for how we set this problem up. We used what's called semi-supervised classification. And so so this is a labeling problem. We're given an article and that we found, say, on the internet or something, and we have to label it as a real article or a fake article. Here I'm being a little loose and equating fake with machine written. Now, one thing I want to say also is that you can do the same setup for human written news, human written like fake news versus human written real news. But it actually gets to that same issue I was talking about earlier about how human written fake news is really easy to detect, but using machines. You don't need to understand what this actually says. Some people in my group, such as Hannah, like this project led by Hannah Rashkin, did some research and found essentially you can just look at these what are called n-grams, which is like a sliding window of words. If you see the words based on medical fraud, that's just not an n-gram that tends to appear in the New York Times, for instance. So in other words, human written fake news has these like stylistic watermarks essentially that doesn't that it's more based on style rather than semantics. And so it's actually pretty easy to detect that. So, but one other thing is that Grover written text isn't trained on any fake news at all. Instead, what it's trying to do is better fit the distribution of n-grams or style that it sees in the New York Times, just generating what it thinks is the most likely New York Times article that has the headline something like vaccines have been based on medical fraud. And so, and then, if you go back and generate a headline again, it'll probably be something slightly different, but that sounds more realistic. So we can't use these techniques on Grover. Okay, so back to the semi-supervised classification setup. So what we're going to do here is consider 5,000 examples from a Grover adversary, 5,000 real news articles that were published relatively recently. This was back in 2019, so they were recently then. And we're going to consider unlimited real news articles that were published way in the past. So this kind of seems realistic because it's like you have infinite data for the past, but recently, like over like the last, maybe you're trying to scan for like recently published news articles, and so you have like some recent articles that are human written and some recent articles that are machine written. So that's the setup we're using. And so we consider some pre-trained neural discriminators. So these are, by discriminators, what I mean is in a very ML setup of a model. These are just classifiers, essentially. I probably should have used better terminology, but yeah, it's also called a discriminator. And so there's a couple, BERT, GPT, and Grover. I'm not going to get into these details, but essentially the way that these things work is that they were pre-trained, which is where they have representations that they build up over essentially applying some variant of the language modeling objective over lots and lots of data. And this gives you like some kind of like a representation of the sentence or the article, if you will, and then you can use those to better predict for new tasks given like a little bit of data. So this is kind of a pre-training, fine-tuning setup. If you've chatted about that before, maybe similar to like ImageNet, you can pre-train a classifier there and then fine-tune it on different tasks. Okay, cool. So going a little faster, I wouldn't say this is, I'm not going to go too much into this, but essentially what we found is, so we compared all of the different discriminators versus all of the different generators. And what we find is that, so BERT is able to detect or classify real news versus Grover written news 76% of the time, GPT 78% of the time. And now the Grover large model with the same number of parameters gets 91% accuracy. And if you had more parameters, or if you just train the model for longer, or say on more data, you get like 98% accuracy. If you have the same number of parameters in the 1.5 billion regime, you get 92% accuracy. And we found kind of one big takeaway here. So these accuracy results are pretty high. And what we found with like some more experimentation is that they're actually very loose. And so by that I mean you can pre-train the model, just give it more data that isn't as good. Like you can just generate more examples that aren't from the exact generator that you're trying to detect, but you could just to give it more training signal, and then that number will go up even more. So it seems like what's kind of going on is that it's not a hard problem for the model to be able to classify, to tell the difference between news articles that were written by a language model and news articles that were written by a human. And so that's kind of the big result. This is actually not hard. So and I want to mention also, I don't know if I made this really clear or not, we're considering the setup where the discriminator, the classifier that's doing this detection, has different parameters than the generator. So it's not just like, oh, I would give this sentence a very high probability, so I'll spit it out during generation, and then I would also learn to like predict the opposite of what I would generate, if that makes sense, like during classification. These are just independent models. So this is our key takeaway. And that means it's actually kind of good on the prevention side. Grover is a good defense against other Grover models. And so maybe like taking a step back, like how comfortable should we be with this conclusion? And we did some more investigation as to why this why this problem is a fundamentally easy one for models. And it all gets down to this one issue, and I'm not going to go too much into this, but it's called exposure bias. And so by that I mean the model is only trained to generate the next word given human written text, and it's not perfect, so its generations are just going to get progressively worse over time. Maybe one way to kind of think about this is like, imagine, you're driving a car, but suppose you learn how to drive a car, never by like a whole sequence of actions, just like each individual like second, are you like turning the steering wheel left or right? You know what I mean? And then you could imagine like if you're if you're doing this and your way of driving, I guess, is not trained on a long sequence of actions, then you might imagine you'll get quickly off track and you won't know ever how to correct yourself. You might be driving down the wrong side of the road, for instance, and because you have no idea about what driving actually is, you're just like learning how to mimic um, expert actions by someone who knows how to stay on the right side of the road. Um, you'll probably get into an accident. So it's kind of the same thing that happens here, if that made sense. And if not, I can answer more questions. And so there are some hacks to correct for this, but these hacks also leave noticeable signal. I'm not going to get too much into why that is, but essentially, it's kind of Grover can just pick up on those hacks and then be like, okay, well, real articles don't have those hacks, so I can tell the difference there. Sorry. Let me. Okay. Sweet. Okay, so overall, summing up just the Grover section, Grover is a strong generator of neural fake news because it's not doing anything magical. So this language modeling objective we were talking about earlier, it heavily rewards style over substance, which is why you can do these like style transfer situations, like generating fake news articles that are written like the New York Times. And the model isn't perfect at this objective. It veers off the manifold of human written language, if that makes sense, which makes it easy for models to tell it apart from human written news. So maybe I want to talk just a little bit about kind of the ethical policy implications. And so we kind of started talking about this back in 2019. And our position then is, okay, the danger of these language models is limited now, or I guess in 2019. So we should study them. And we should study them in a collaborative way with security researchers, ethicists, and policy people, and so on, so we can come up with good norms for safe model release. Like, how can we release models in a safe way that doesn't do harm, especially to marginalized groups? And then sort of what happened is this. So people groups just released bigger and bigger models, even bigger than Grover GPT-2. Google released T5 with 11 billion parameters, 11 million parameters. No, wait, what? Sorry, 11 billion, parameters. And then this year, fast forward another year, OpenAI released another model, GPT-3, with like 175 billion parameters, and they instantly made it available for commercial use. So there's some key issues here that I don't think we're really ever fully resolved, and that we're kind of still grappling with. And so the key one, I think, is this. So how do we set good community norms for release and research on text generation and for AI in general in a way that doesn't create harm, especially towards people from marginalized groups? And especially considering that OpenAI is trying to sell this, and other groups probably are trying to sell these big models and use them in production right now. And I would say it looks like the current incentive structures don't work. Sort of people in academia and industry seem to be incentivized to create larger and larger models. They cost a lot of money, and they in fact have a huge environmental cost in terms of the electricity needed to power the training of these models. It's like I don't know the exact numbers, but it really is quite a lot. And OpenAI burned like at least like $10-20 million in compute training GPT-3, and who knows, they could just we don't really have good norms that would incentivize or disincentivize them from creating a bigger model that does pretty much the same thing. And one other issue I would argue is that this language modeling objective is inherently a fake news objective. What it's doing, this probability term seems so innocent, right? And what it's really doing is it's saying, a model should assign a high probability to every piece of English text that's ever existed, ever. So that means like it should give high probability to like, we want to learn a writer that can write everything that was ever published on Fox News, everything ever published on the New York Times, and so on. And that's kind of ridiculous because that's not how humans work. Humans understand language not by mimicking every other writer in existence, but just kind of like learning their own path of how to communicate and meet their own objectives that fits their own values. So I would argue that sort of this is kind of the wrong objective. And it's kind of silly that we're just learning how to mimic everyone else. Silly, and I would argue somewhat harmful. So maybe one other piece of like one other shameless plug, which is one other thing that I've been working on, and we released it on archive this year. And the idea is, okay, well, I think so. Personally, I think the language modeling objective, there are some really key issues there, and I think that we're going to want to move away from it going forward, even though it's proved pretty useful in the past. So what I think we should do instead is evaluate a natural language understander or generator based on how well it fits the objectives we want language understanding models to do. And so in this case, how well does it help people in need who are asking this model for advice? And so we have this paper. There's some other social good issues that I could talk about, but probably we want to leave this space or this time for questions about Grover and stuff. But it's available. You could just, it's on archive, evaluating machines by their natural language use. Or maybe, sorry, maybe I think it's real world language use. I don't know. Yeah. Cool. Okay. So conclusion, threat models, attacks, defenses, all important. Grover is the best defense against itself. However, it's no panacea, and there are some issues with this defense in the long term that we're still that are really important and that I could talk about more. Going forward, we need collaborative AI security policy research, and that's why we released the model rather than keeping it private, or even worse, selling it to the highest bidder. So that's it.
Awesome. Thank you so much, Rowan. As has been tradition, I'm going to, if I can, unmute everybody and ask everyone to physically clap. Cool. So thanks so much. And before I turn it over to questions, I just want to say, everyone, thanks so much for joining us for the last couple of workshops. This is the first time we've done this sort of workshop series thing, and it's been really fun. It seems like it's something that people are interested in. We're going to see if we can organize something like this again. But I also wanted to plug specifically for Stanford folks, CS plus social good as an org in general. As you can see, this is the org that we founded this class through, that we have open source as a workshop. And if you are interested in any sort of intersection between CS and social good, whether it's like public interest tech or what we've worked on in AI for social good applications, AI for social good is just one of the many initiatives that CS plus social good has. So as you sort of start the school year, please keep the club in mind. I'm sure you're going to get a lot of and okay, so with that, I am going to turn it over to questions. So please ask any questions for Rowan in the chat, or raise your hand and I can unmute you.
One thing I was curious about is how the Grover model and how you in training time actually handle the case of different types of fake news. So it's like a difference, like human-generated fake news, like actual versus like random text, for example, whatever it is.
Yes, that's a great question. So what we did when we were collecting the data to train Grover on is we only used a subset of domain, like we used domains that were indexed by Google News. So that's not perfect, but it's like a good, I guess, precision-oriented list of domains. And we just like scraped a bunch of common crawl news articles from those domains. So I think that did a good job of, rather than just like say what OpenAI did, where they just trained their model on just random text that they downloaded from Reddit. We were a little more selective in that case. So that gave us just news articles, and we believe just real news articles, though there are some iffy cases. I think we probably have like Breitbart in there, so that's not really news. Actually, I'm not sure about that. But anyways, I think also indexing it by domain, like having the domain be part of the thing that the model sees is pretty important. So that way the model can learn to do different things based on each domain. But yeah.
There's a question in the chat from Didi.
Yeah.
Does this work with Grover, defending against Grover, translate to other models like GPT-2 or GPT-3? Which is a great question, especially since GPT-3 is incredibly good at writing convincing text.
Yeah, that's a good question. So what we found is that uh, we did some additional experiments with GPT-2 and found that Grover can detect GPT-2 written news articles in a zero-shot setting. So it was never trained on GPT-2 written news articles before, but it's able to just flag them as machine written like 96% of the time. So that's pretty high. Now in GPT-3, we don't know. Actually, I don't even have access to GPT-3. I think some other people in my group do. I don't think it would do as well, but I don't think it would be. I don't think it would be like fully random. Uh, so yeah, so sort of like what seems to be the kind of the trend here is that the difference in model size is captured like in terms of performance, it behaves logarithmically, which means that so GPT-3 is, I guess, 100 times bigger than Grover. However, it doesn't really do 100 times as well. More like a little bit better, if that makes sense. It just costs 100 times more to train. Actually, over 100 times, I guess. Yeah.
Awesome. There's one more question in the chat.
Yeah.
Let's see. Are there differential privacy techniques to prevent language models from plagiarizing source texts?
Oh, that's a really good question. I'm sure that there's some people who are working on differential privacy applied to language model training. I'm not fully aware of how that space works. One thing I found though, it seems that these models actually, surprisingly maybe, don't actually plagiarize that much. And this is this common trend that a bunch of people are finding. Um, but they're so loose, I guess, with the facts, right? And this is why the whole fake news thing happens, right? Like the model is not really trying to like the model doesn't actually um, the model's probability distribution is trained to be as close to the real probability distribution as possible. But that probability distribution is very vast and very open-ended. So there's often a lot of different things you could say, which means the space of potential articles that could be generated is pretty large. So in other words, it doesn't seem to copy that much, except for like some key things. Like you could probably like give it some like song lyrics, and it would probably like finish them for you. Like because it's probably seen that a lot in the training set. If that makes sense.
Cool. And I actually have a question.
Yeah.
Speaking of plagiarism, do you see like the biggest threat from these sort of models, especially from Grover, that's able to like take this metadata as an input? Do you see the biggest threat as like just being able to generate text, whether that's propaganda or not, or do you think that one of the bigger dangers could also be like writing something in a voice that's convincing of like a well-known writer? Similar to how like Karan showed like this is Obama talking, but it's actually not. Someone could claim that this is something that like some writer has written when they haven't.
Yeah, I think that's a good question. Honestly, I think it's hard to say, oh yeah, this specific use case is more dangerous than this specific use case. I think if there's one thing that I'm most concerned about kind of is the whole landscape of the community, how it seems like we haven't set up good, in my opinion, we haven't set up good norms such that the research that's done is aligned with uh, social good objectives, if that makes sense. So it's possible that both of these, that like some of these things are like there are some I don't know. It's possible that plagiarism is like a bad thing, but it seems like the problem that I see is that um, companies and researchers are just incentivized to make numbers on data sets or on like benchmarks and stuff go up, so they can like commercialize their products. And so what that means is that people don't really think about the social, like they don't have an incentive to think about the social impact of the systems that they build.
I guess
Yeah.
follow up. How do you
Yeah.
think it's possible to even incentivize like corporations or like even academic research labs to focus more on like the end-to-end application and like the societal impact that their work could make as opposed to just like seeing the number go up?
Yeah, that's a really good question. And I really don't have the full answer on that. I think that I think it kind of behooves us as engineer researcher type people to like actually organize, because I think so there's a lot of talks and stuff floating around, well, we should all think about our personal impacts. I think that's good, but I think we should also kind of recognize that under the current landscape of like funding and the market kind of, people like people are incentivized to do things that doesn't represent, I would hope, are our collective values. And so I think like I don't know, I think that's kind of where I'd like um, the community to move. But I feel like that's going to be hard because especially in like the world of like tech, everyone, the dominant like paradigm is for people to think more individually, which obviously is very much to the benefit of these companies that just want to make a lot of money. So that's my thought. But I don't know.
That's true. Yeah, it is sort of more of an institutional issue, I suppose, rather than just like an individual thing.
Yeah, but we're individuals who can organize together, and so I think I don't know. I feel like there's organizations like the Tech Workers Union that are trying to build momentum, and I think they're doing a good job, and I'm really excited to see that move forward.
True. Great. Awesome. Any other questions in the chat, or anyone want to raise their hand and ask a question on Mike? Got one question. Yeah, go for it, Kamal.
Well, with Grover, when you're talking about identifying fake news and also creating fake news, were there different subjects that Grover was better or worse at for both identifying and creating fake news for that?
Oh, that's a really good question. So in fact, actually, yes. But it's not the way you might think. It's not that like, oh, I don't know, sports news is like easier or harder necessarily than like, uh, I don't know, like TechCrunch articles. But what I found is that there are some websites that kind of are already AI written. That doesn't mean they're written by GPT-2 or Grover, but they kind of have these like templates. A lot of it's like financial news, and so these are they're kind of template written articles that are like, the stock for Google rose 10% yesterday. The stock for Microsoft went down 5%. And so if you can memorize these templates, these are actually a lot easier for Grover to learn. And at that point, it's Grover to learn to generate. And at that point, it's actually really hard for Grover to tell these kind of machine written articles that were written by a template versus telling them from Grover written articles that are just mimicking that. So those articles are easy to identify. I'm sorry, those articles are easy to fool, but real articles that are written by people without templates, those are hard. It seems like no matter what domain, I guess, if that makes sense.
So there basically has to. So if there's a template for like reporting economic news, then it's going to be easier to pick up on that template as opposed to.
Yeah, easier to spoof. Yeah, harder to detect.
Okay. Because then Grover can detect that template.
Sorry, Grover. Yeah, Grover detects. Well, Grover learns to generate that template very well, such that the only way you'd be able to tell the difference, I guess, is if you actually had the ground truth, like stock numbers that day, if that makes sense, which Grover doesn't have.
Well, that's interesting. Thank you.
Yeah, no worries.
From Evelyn.
Yeah. So this is kind of a weird question, but it sounds like you've been pretty critical of OpenAI throughout this talk, and my impression as a relative outsider is that they like are concerned about like the direction of AI going well and have been leading the discussion about publication norms and like the ethics of releasing language models, especially. So, what I guess like what gives for you?
Yeah, that's a really good question. I guess so. I don't. I guess I should clarify. I don't have any like. What is it? I think that. So I've met with people who are at OpenAI. I think they're good people. I think they have a mission statement. Now that said, they kind of a year ago or so they transitioned from a nonprofit to a for-profit company or a capped profit company, I guess.
Okay.
And so at the end of the day, this is what I kind of see as also an outsider to OpenAI and how they work. They need to somehow make money. That's what it seems. And I think for that reason, it seems to me, and also kind of some other people in the community that like, it's not clear that they've really reconciled their profit motive from the ethics and bias and like uses of their commercial product, if that makes sense. Obviously, I think every company has to navigate that in today's world, and I'm not sure that by just immediately commercializing their biggest model, they did a good job of that. But that's just my take.
Okay.
Yeah.
Yeah. Thanks.
Yeah. No worries. Happy to chat more about this offline.
Cool. Any other questions from anyone? That we can wrap this up. I know we're running a little bit over. Awesome. Yeah, I think that's it. Yeah, so thanks again so much for everyone for tuning in. Yeah, it's been such a pleasure to host this workshop series. And we'll be sure to send out the slides and the recording and all the other resources very soon. So thanks again, everyone. And I will be signing off.